All right, so hopefully at this point you feel comfortable with stoichiometric calculations, converting from, for example, moles of one substance to the mass of another. That's what you were assessed on with your quiz, and most of you appear to have a very solid understanding of that concept. So we're going to continue with our overarching learning goal up here. You've already got the conversion down. We're going to identify and explain the importance of limiting reagents today. We'll do that either by explaining how to make an ice cream sundae or pizza or whatever it is you want to make. From that, we'll be able to calculate theoretical yields, and then next time we'll get into percent yields, actual yields, and also carrying out the experiment in the lab. So next class you'll have your lab on limiting reagent, theoretical yield, percent yield, etc.
Can we make ice cream?
Sure, why not? Let's make ice cream.
Wait, like real ice cream?
Well, first we're going to make a sundae on paper. Oops.
We're going to draw it.
I'm totally going to do ice cream on paper. Like, you think I'm kidding.
Wonderful. What we want to start with today are reactants that are limiting or in excess. A limiting reagent is one that's used up completely, and it determines how much product you make. And I will explain that to you very simplistically. The reason why you have limiting and excess reagents is because in a chemical reaction, it's very difficult to get every single atom to react. And so typically, one of the reactants is in excess. There'll be some left over. The other is limiting. It will be used up completely. For example, want to make an ice cream sundae or a pizza pie?
Ice cream. Ice cream.
Ice cream sounds good. So, for my ice cream sundae, I need a bowl. I need some ice cream.
Wait, what's that third thing?
That's whipped cream.
That's an upside down tornado.
I need a cherry. And we need sprinkles. I have 10 bowls, 20 scoops of ice cream. Oh, stop it. 30 servings of whipped cream, 15 cherries, and 50 servings of sprinkles.
50 servings?
Sure, you get the big tub. That's what we have in my house. And we, wonderful. We are going to make that's whipped cream. And there's my ice cream sundae. I put the sprinkles on. Here, we all have chocolate sprinkles. Is that better? Oh, boy. Now, we have our ice cream sundae. How many ice cream sundaes did we make if one ice cream sundae, or let me rephrase, how many can we make if one ice cream sundae requires one of each of these? 10. Okay? Hang on. So what we've got here, the bowls would be considered our limiting reagent, and it's just the bowl, not the amount, but the amount determined that the bowls were in limiting supply. We were going to run out of these first. The limiting reagent determines how much product you can make. The other substances are all in excess. I will use 10 scoops of ice cream, and I will have 10 left over at the end. How many servings of whipped cream will I have left over at the end? 20. How many cherries? 5. And how many servings of sprinkles? 40. So the limiting reagent gets used up completely, and it determines how much product you can generate. And therefore, the limiting reagent determines how much product you can make, and it has to be used in our stoichiometric calculations. The only new piece today is figuring out which reactant is limiting. The actual calculation to figure out how much product you can make is the same as you've done previously. Now, the amount of product you can make is known as the theoretical yield. The theoretical yield is the amount of one product that can be generated. It's the amount that should be generated, what you would generate in a perfect world. In the lab, we're going to also deal with actual yields, and that's how much product you actually made, and that will be the mass in grams. Typically, the theoretical yield is the mass in grams unless specified otherwise. You can have theoretical yields as moles, volume, etc. But if it just says theoretical yield, typically it's the mass in grams. So the limiting reagent is the substance that's used up completely. It determines how much product can be generated. It's used in the stoichiometric calculations. And a lot of what I said is indicated on the screen in your notes. How much product you can make depends on the limiting reactant. The limiting reactant gets used up, and it must be used in the calculations, and we'll point that out when we get there. The amount of product that should be generated is the theoretical yield, typically the mass in grams. There are a number of ways to determine which reactant is limiting and which is in excess. Previously in problems we've been doing, you've been given one quantity. For example, 5.75 moles of rubidium. You knew what the given was because you were only provided with one quantity. Now you're going to be provided with two quantities, and you have to figure out which reactant is limiting and why. And that's what you will need to do in order to be successful in these type of problems. And typically the quiz you just took, it would never be set up so simplistically. You would always be provided with two givens, and that's why I'm just going to do the one remedial quiz where you could test back into either. There are several steps that you follow to determine which reactant is limiting and which is in excess. You always have to determine the number of moles of each reactant, and these will be relatively simple. You'll have two reactants. You could have more than two. That would make it far more complicated. So if they give you mass, you must convert to moles, which you already know how to do back from chapter 7. If they give you moles, it's a little bit easier, and as we get started with this, I'll initially give you moles so that you don't have that other step. You need to calculate the mole ratio of what's given. So you have to compare moles of each substance based on what you've been given and look at the ratio. You will compare it with the mole ratio of the reactants from the balanced equation. That's what you need in terms of the substances reacting in stoichiometric proportions. The key to being successful here is you must compare moles. If they give you grams, you better convert to moles, and you'll see that shortly. But the only way to compare two substances is through the mole ratio, and that we talked about previously, and it's going to be critically important here. This piece is a little tricky. I will explain this piece as we go in far more detail. It says the one in which more substance is provided than what it would normally yield is in excess. That is to say, if you are given a quantity which is greater than what you need from the balanced chemical equation, then that substance will be in excess, the other will be limiting. If you're given less than what you need then that substance will be limiting, the other is in excess. I'll explain that with our example because it won't make sense till we get there. It says the easiest way to compare moles based on the stoichiometric coefficients is to divide each reactant's moles, that is what's given, by its coefficient. Whatever you have less of is going to be your limiting reagent. And I'll walk you through all of these pieces in this first example. The other thing that you'll be able to do is you'll figure out not only which substance is in excess, but how much of that substance doesn't react. It's just left over. And typically with limiting reagents and excess reagents, typically the substance that's cheaper or recoverable is the one you use in excess. The one that's expensive you don't want to waste, so that typically is the limiting reagent. In the lab, you'll be reacting sodium bicarbonate with hydrochloric acid. One substance will be limiting, one will be in excess. The limiting reagent determines how much product you will make.
What happens to the excess, or like what does it look like in a chemical reaction?
It's not that it looks like anything per se, it just is present at the very end of the experiment. So if it's recoverable, you can then get it out and react it further if you want to. Sometimes if you have way too much excess reagent in your chemical reaction, it can affect your theoretical yield because it would, let me rephrase, it can affect your actual yield, not your theoretical. It would affect your actual yield because then when you massed out your product, you'd have some reactant hanging out there at the end. So it wouldn't affect your theoretical yield, your actual yield. Your theoretical yield is based on the quantities you've been given. You figure out your limiting reagent, and from it you can determine your theoretical yield. That's what you make in a perfect world. The actual yield is what you make in the lab.
Is the theoretical yield like the 10 from all of them combined in the ice cream
Right.
example?
Right. That's your theoretical yield, exactly. The 10 of the final product.
Yeah, the final.
Yes.
Just the bulk.
Mm-hmm. You can also figure out how much of the substance is in excess. This I'm going to come back to in a little bit. This is a little advanced for honors chem. It's in your book, but it's a little bit much. I'm going to show you how to do it, but it would only be assessed for extra credit. Okay? All right, let's walk through this example very slowly so you can see all of the little pieces that I've mentioned already. It says 1.21 moles of solid zinc are added to 2.65 moles of hydrochloric acid. Zinc chloride and hydrogen gas are formed. So right away, you should see that you have been provided with two givens, 1.21 moles of zinc and 2.65 moles of hydrochloric acid. They want to know what reactant's limiting, LR, what's in excess, abbreviated XS. They want you to calculate the theoretical yield, that is the mass of hydrogen gas that should be generated. That's the mass of product. If they ever say theoretical yield, it has to be a product. And one of the things I know some of you were tripped up on the quiz, if a substance is generated, is it a reactant or a product? Has to be a product. If it's consumed, it's a reactant. And then finally calculate the mass of unreacted excess reagent. So there's a lot going on here. Let's simplify. You have the balanced equation already. And so in your notes then, what we're looking at, let me go a little bit bigger. We've got zinc plus hydrochloric acid generating zinc chloride and hydrogen gas. And you ran this lab earlier this year. Single or double replacement? Single replacement, good. Okay, the other information that was given is that you have 1.21 moles of zinc and 2.65 moles of hydrochloric acid. Those were both given. We want to know which reactant is limiting and which reactant is in excess. These are the given. My need is based on the stoichiometric coefficients. For every 1 mole of zinc, 2 moles of hydrochloric acid will react with it. So it's a 1 to 2 mole ratio. So there are a couple ways to do this. I like to look at it and see if I can match that ratio, or if I can, is it less than or greater than? So I see a 1 to 2 mole ratio here. What is 2 times 1.21? 2.42. So for every 1 mole of this, I need 2 moles of this. So 2 times this is 2.42. Am I given more or less than what I need? Comparing 2.65 to 2.42. I'm given more. 2.65 is greater than 2.42. So I'm given more than what I need. Hydrochloric acid is in excess. Zinc is the limiting reagent. Now some kids see it right away, some kids don't, and it's fine. Let's make it simpler, and there's a lot of ways to do this. I can divide each one by its coefficient, and that makes 1.21 moles of zinc and 1.32 moles of HCl. Which number is bigger? The bottom one. So 1.21 is less than 1.32. Whatever you have less of after you've divided by the coefficients must be the limiting reagent. So zinc is the limiting reagent because, now go back to the original given, 1.21 moles of zinc is stoichiometrically going to be fun to spell. Less than 2.65 moles of hydrochloric acid.
Do we have to know how to spell that for the
I'll take stoich. It's just stoichiometrically. You guys are good spellers. Not that good, huh? You underestimate yourselves. That will earn you full credit on the determination of the limiting reagent. Let me note a couple things here. A substance is a limiting reagent, not an amount. You can also say that zinc is the limiting reagent because you have more than 2 times as much hydrochloric acid as you do zinc, or you were provided with more than 2 times as much hydrochloric acid as zinc. That's fine too. Some of the kids just like the quantities straight up. Whatever's easier for you is fine. Questions here?
What would the problem on the test be asking? Like, what is
The problem on the test is going to say which reagent is the limiting reagent and why.
So can it say it like the opposite? Like, which is the...
Excess and why? It could, but I'm telling you right now, I just wrote your quiz. Which reactant's the limiting reagent and why. But that's a good point. As I walk you through this, we do it in baby steps because it's easier for you. Some of your problems on your classwork, certainly textbook problems, they're not going to ask you what the limiting reagent is. They will provide you with 2 givens, and they will just ask you for the theoretical yield of a substance. But you have to know to get the limiting reagent. So be careful there. I walked you through more simplistically in your notes and on your quiz.
So would the theoretical yield here be 1.21?
No. The theoretical yield, which is the next part of it, says calculate the theoretical yield, and it says mass of hydrogen gas that should be generated. Again, a yield, you have to yield a reactant or a product. Product. You have to yield a product. Be careful there. If they ever ask you for theoretical yield, you're going after a product. If you're talking about what's generated, you're going after a product. And I tried to write your quiz a little easier than in previous years to try and eliminate that confusion. So now it says calculate the theoretical yield of hydrogen gas. That just didn't come out right. Theoretical yield of hydrogen gas. So we're looking for the mass of hydrogen gas. Now, based on everything we've talked about, do you think that we should use the limiting reagent or the one in excess? What determines how much product you make? The limiting. So now we go back to the original limiting reagent, which is here. And it's not hard, you just have to focus. You can do it. We have 1.21 moles of zinc. From the balanced equation, 1 mole of zinc to 1 mole of hydrogen gas. Please stop flipping the water bottle. Whenever you're given moles, your first step is always the mole ratio from the balanced equation. You already know how to do this. The mass in grams from the periodic table. And that's 2.44 grams of hydrogen gas. That is the theoretical yield. That's what you can make in a perfect world. That's what you should be able to make.
Why is it 2? Why isn't it 1.009?
Because you have H2.
Oh.
So the theoretical yield is what you should be able to generate in a perfect world. However, typically you don't generate as much as the reaction predicts for a number of reasons that we'll get into next time. The other piece of this says calculate the mass of unreacted excess reagent. This is a little trickier. I'll walk you through, like I said, strictly for extra credit, so don't stress over it. But we'll do several, so you should be able to do it. So we're given 2.65 moles of hydrochloric acid. We know hydrochloric acid's in excess because the other substance is limiting. For every 1.21 moles of zinc that you have, how much hydrochloric acid reacts with 1.21 moles of zinc?
2.42.
2 times that, right? You could set up a mole ratio problem if you wanted to, but clearly you can see for every one of these, 2 of these react. So if you have 1.21, then this has to be 2.42. So in terms of what reacts, you have 2.42 moles of hydrochloric acid. If you subtract the 2, this is what is unreacted, hanging out in the reaction vessel. Yep. And they asked for mass, so very simply convert it to mass. and you have 8.4 grams of HCl that is unreacted at the end. As I said, this would strictly be for extra credit. We'll do more of this, but we're not going to stress over this piece, determining the limiting reagent and the theoretical yield, critically important. And we're going to do several examples just like this, and hopefully by the time we go through, you'll have a feel for it. And then once you do some additional problems, you should be golden with this concept. All right, so in the next problem, we're going to work through this. We've got 7.24 moles of magnesium and 3.86 moles of oxygen gas mixed to generate magnesium oxide. The first piece says write the balanced equation. So what would be our balanced equation? What reacts with what? Go ahead, Josh.
I didn't see it.
What reacts with what? Back on the screen.
Oh, hold on. I have it now.
Okay.
Yeah. 7.24. Oh, so it's, yeah, magnesium and then 3.86 of oxygen gas.
And what is it for?
Magnesium oxide.
All correctly formula written, correct?
Yeah.
Okay. Now, you're given moles. And when you're finding the limiting reagent, you always must compare moles. Now, right now it's cake because I'm giving you moles. Soon you know I'm going to give you mass because that's what we do in the lab. So I have moles of each one. How do I figure out which substance is the limiting reagent?
Divided by 2.
You're going to divide which one by 2?
Magnesium.
Why? Because of its coefficient, all right? So we're going to have 3.62 moles of magnesium. And what would I divide the oxygen by? 1. So which amount's less? The magnesium. So what's the limiting reagent? So magnesium is the limiting reagent because, go back to your original givens, 7.24 moles of magnesium is stoichiometrically less than 3.86 moles of oxygen gas. And the word stoichiometrically is important there because clearly this quantity doesn't appear to be less than that, but it's stoichiometrically less. Alternatively, you could look at the one that has a coefficient of 1 in the balanced equation. You could double this, and you'll see that this is not 2 times as much as this. It's less than that, and therefore magnesium is the limiting reagent. You could indicate that the amount provided of magnesium is not 2 times as much as that of oxygen. Okay? Once you have that, so this would be B, and in C they're asking for what mass of magnesium oxide should be generated, that is the theoretical yield. what do I start with? The limiting or the one in excess? The limiting. You always, 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 always use the limiting reagent to figure out the theoretical yield. Okay, so I have the limiting reagent now. I know it's magnesium. Do I start with 7.24 moles of it or 3.62 moles of it? The beginning. Go back to the original given and begin there. The limiting reagent determines how much product you can generate. If you're given moles, what must be your first step? Mole ratio from the balanced equation. And here's where I would reduce. It will make it easier. And then 1 mole of magnesium oxide, and the grams of magnesium oxide is 40.304 from the periodic table. And again, you're really not doing anything new here other than starting with the limiting reagent. This is exactly what you were just assessed on and appeared to be quite successful with. And that's 292 grams of magnesium oxide. Now, in terms of how this question might read from a book question or some classwork questions, your classwork's far more challenging than your quizzes, but that's okay. You'll be very ready. Very often they will just say to you 7.24 moles of magnesium and 3.86 moles of oxygen gas react. And then they'll just ask for the theoretical yield of the product. So they won't tell you to write a balanced equation. They won't tell you to determine the limiting reagent. You have to know to do that. Your quiz is set up far more simplistically so that you can be successful there. Okay? The next question's grossly similar with one key difference. In the laboratory, you are not given moles of substance. You are given a substance, you are given a balance. What unit? You would have grams. So we determine mass in grams using balances in the lab. And in the lab, you're going to be reacting sodium bicarbonate, which is baking soda, with hydrochloric acid, and you will then generate product. You'll determine your theoretical yield, your actual yield, and then you'll see how good of a job you've done. And in general chemistry labs in college, typically the only thing you're graded on is how much product you make and how it compares to what you should have made. So what was your percent yield, which we'll get into next time. So in regard to number 2, this is similar with one key difference. You're given mass. So let's take a look here. It says 68.2 grams of sodium oxide are mixed with 138 grams of calcium nitrate. Write the balanced equation. Raise your hand and help me. Go ahead.
Would be Na2O.
Yep.
And then Ca.
Says calcium nitrate.
Yeah. Ca.
Like that. What's missing? Oh, you can't see anything.
Oh yeah. I know 3, 2, 2.
You need a 2 here, right?
I know 3 too.
Okay. And what are you going to make?
And I can't still see it.
Doesn't matter, it's double replacement. We discussed that. In double replacement, the activity series is not relevant. It's only relevant in single replacement. Some of the kids did that on the test. For the double replacement, they wrote no reaction. That was a no-no. So you're going to make
NaNO3,
yep.
and then CaO.
All right, so this one's really, really straightforward because your mole ratio of reactants is what? 1 to 1. That's going to make life very easy. In the lab, it's going to be that way too. 68.2 grams of sodium oxide and 138 grams of calcium nitrate. And the first thing you need to do is convert to moles, because the only way you can compare two different substances is through the mole ratio. So sodium oxide, 61.979 grams. Got to be in the denominator to get it to cancel. 1 mole on top. 1 mole of calcium nitrate. Formula mass from the periodic table. So if you're given mass, which you will be, you need to convert to moles. Otherwise, the game's over. It's a complete bomb if you compare mass. Now in this case, the coefficients are both 1, so you don't really have to do that. I'm still going to throw it in so you don't forget. What's greater than what? The 1.10 moles of sodium oxide is greater than that. So what's the limiting reagent? So calcium nitrate is the limiting reagent because (138 grams of calcium nitrate, go back to the original, is stoichiometrically abbreviated less than 68.2 grams of sodium oxide.
Is that 2B, or that's still A?
That would all be which reactant is limiting. Yep. I don't know. It says calculate the mass of unreacted excess reagent. Again, this would be for extra credit. But we'll go ahead and look at it. Which substance did I make a mistake?
No.
Okay. Which substance is in excess?
Sodium.
Has to be the sodium oxide, right? So we're given 1.10 moles of it. Huh?
What is that thing you circled?
That?
Yeah.
That's like a little Roman numeral 1. Baby Roman numeral 1.
Gotcha.
How much of that reacts? How'd you get that?
It's the limiting reagent,
So,
so you can't do more than that.
right. So if 0.841 moles of this react, that's the limiting reagent, it's used up completely. With the 1-to-1 mole ratio, then the same amount has to react with it. So if you subtract the two, you'll get what didn't react. And then you just convert to mass. And this actually is very simplistic because you already have the formula mass from here. And that would be 16 grams. Down to 2 sig figs. All right? But again, this would strictly be for extra credit. If you're not fully seeing it yet, we can do some more, but don't stress over it. At this point, you want to be able to determine the limiting reagent, explain why it's the limiting reagent, and then also you need to be able to determine, you want to be able to determine the theoretical yield. It says, what is the theoretical yield of the sodium-containing compound? What am I solving for?
Sodium oxide.
What am I solving for? The theoretical yield, so a reactant or a product? Product of the sodium-containing product. So what am I doing? Sodium nitrate is correct. And what do I start with? My limiting reagent, which was? Which was? Look at what you wrote. What's the limiting reagent? Calcium nitrate. How many moles of calcium nitrate did we have?
2.
No. What were we given? 0.841. And now this is a mole to mass problem, which most of you have mastery in. For every 1 mole of calcium nitrate, you generate 2 moles of sodium nitrate from the balanced equation. For every 1 mole of sodium nitrate, that's 84.994 grams of sodium nitrate. And what'd you get? 143? Sounds good. All right. So hopefully you feel comfortable with stoichiometric conversions. You should be comfortable with that after having just taken your quiz. Your goal for today is to understand what a limiting reagent is, what it determines, how to determine what the limiting reagent is, and how to calculate your theoretical yield of substance. A theoretical yield, you have to focus on a product, and that's what you'll get some practice with now. What I'm going to ask you to do before you even move is you want to be able to do number 3 from start to finish. So in the next 5 minutes, you're going to sit and try and work through number 3. I'll show the answer in a few minutes. Also on your classwork, you want to be through number 6 before the next class. You already went through 5. So all I'm asking you to do before the next class is number 6. And you guys actually have 24 minutes, which should be more than enough time to do question number 3, as well as number 6 on your classwork. I will put the answer to number 3 up in a few minutes so that you can check as to whether you have done it correctly. But that's what you want to make sure that you can do. Now I'm going to flash the answer on the screen so I catch it on tape, so nobody's looking up right now, right? You're all looking up. Don't look up. Look down. You have it in your notes. Look down. If you don't have your notes, close your eyes for 5 seconds. Don't look up. Don't look up. No, don't look up. I'm going to show the answer. I'm going to put it back up on the screen. All right, you can look now. It's back on the screen. Guys, we have 20 plus minutes. If you have questions, this is your opportunity to ask it. I realize it's 6th hour. I realize it's the end of the day. But if you use this time productively, you will be very successful in this section. This is a critically important concept for college chem, AP chem, etc. Okay? Questions? I don't know. Questions on this? Questions on the lesson?